Good afternoon, everyone. I'm Dr. Mohammad Mehdi Sedaghat from Tehran University of Medical Sciences. And I'm going to talk about classification of larvicide activity of natural products derived from plants against Anopheles vectors, as I'm working in a medical entomology and vector control department in Iran. So let's start with vector-borne diseases. Vector-borne diseases include some of the world's most destructive diseases, many of which are increasing threats to human health as the environment changes and globalization increases. Vector-borne diseases account for 17% of the estimated global burden of all infectious disease. For example, dengue, with a 30-fold increases in disease incidence over the last 50 years. And I'm focusing on malaria, another example of vector-borne diseases, which spread in many tropical and subtropical countries in the world. Malaria caused an estimated 627,000 deaths in 2012. It is difficult disease to control, largely due to the highly adaptable nature of the vector and parasites involved. The vector is Anopheles mosquitoes, as you see. The transmission is due to bite of the female of Anopheles. And this is a life cycle of Anopheles mosquito. As you can see, these stages are spent in the aquatic environment. So we can use larvicide and essential oil as larvicide, as I tell you later. This is some example of a transient water mosquito habitat, or we call them breeding places of Anopheles. The usage of larvicides still remain as the significant method among the other methods for mosquito control. The control of mosquito larvae worldwide depends primarily on application of synthetic larvicides. Unfortunately, the side effects of synthetic larvicides on organisms and the environment are increased. After introducing DDT by Paul Muller, the golden age of pesticides started. And you see, this is from the Time magazine at those days. And people thought the DDT and other pesticides that we call them biocides was really good for everyone. But they didn't aware of the side effect of these biocides. Till Carson profiled many facts of DDT besides its ability to kill disease and agricultural pests. After modern environmental movement, DDT and some harmful insecticides banned in most countries. But now we are still using pesticides. At least 3 million workers poisoned each year, 20,000 deaths per year, with teratogenic, carcinogenic, and mutagenic effects of pesticides. We are looking for alternative for pesticides. Although the usage of plant extracts or essential oils as insecticide can be dated back at least 4,000 years. Botanical insecticides are applied in mosquito control due to their efficacy, degradability, and non-toxic effects on non-target organisms. Recently, usage of plant extracts or essential oils in order to control larval stage of mosquitoes have been investigated by several scientists around the world. We have got 250,000 to 500,000 planet. Among these, just 2014 400 species are useful for pesticide, for pest control, and just only less than 10 species, just only less than 10 species developed commercially. There are several major families of plants that are used for essential oils, especially in my field of study, as a biolarvicides. For example, Myrtacea, Luracea, Lumiaceae, and Astraceae. These are some examples of these. I've done some researches on some of these species. I'll tell you about them later. These are Luracea, you know them, Lamiacea, and Astracea. But we have got a problem with classification of these materials as larvicides. Over the past 3 decades, many reports have described the efficacy of plants' insecticidal properties. It is critical to separate those plants which are really active from others. There is no document or information to classify these materials. There are some few examples to classify, very simple classify of these materials. Let's have a look at this. According to Chen et al. 2003, based on a study on 14 different essential oils on Aedes aegypti or Aedes aegypti, they suggested when oils show LC50 values greater than 100 ppm should be considered as not active, whereas those with LC50 values less than 50 ppm could be regarded as very active. As you can see, there are gaps between these 2 digits. You see, 50 ppm and 100 ppm. Let's have a look at another example. Nazar et al. 2009 tested 100 extracts of plant species for the larvicidal activity on Culex quincunfasciatus. They considered those which showed LC50 value up to 100 ppm as active plants. The plant species were considered as ineffective with LC50 value greater than 100 ppm. They still stick to 100, as you see. In other study, Meseb et al. 2009 evaluated essential oil of 11 plants for larvicidal activities. LC50 values of oil ranged from around 7 to 85. So you see, they just work on these 11 plants and classify these numbers. As you see, they consider the plant species for field evaluation if they had shown relatively a stronger larvicidal effect than others. In another study in India conducted by Shiva Kumar, 2013, they tested 4 plants material against Aedes aegypti. They reported the results as good to moderate effect with LC50 between 90 to 200. As you see, there is different categories or classification. We just propose a classification for larvicidal activity of essential oils on mosquito vectors, especially Anopheles, based on our laboratory and field experiences, and also other descriptive studies or reports. We consider 6 categories for larvicidal activity of plant essential oil. As you can see here, we have 6 classes here. In class 1, we have got extremely active plants, which LC50s are up to 1 ppm. They are really active. We can work on them, and we can move them to the next level. I mean, for field trial, formulation, and so on. In category 2, we have got highly active plants with LC50 between 1 to 5 ppm. In third category, we have got active plants with LC50s between 5 to 50, and moderately active. The plants are moderately active when the LC50s are between 50 to 100, slightly active when LC50 are between 100 to 200, and non-active, we consider plants non-active when the LC50 is greater than 200. Here are some examples of our works that we conducted in Iran. For example, we conducted a study on a larvicidal activity of Eucalyptus commodorensis against Anopheles stephensii, the main vector of malaria in Iran, in Pakistan, and India. As you see, the LC50 values was around 90, which lies in the moderately active class, the fourth category. So I just leave it, and I'm not working more than this on this category. Simple as this. In another work, we have done a study on Cleosa odoratissima. It is a newly plant recently described from Iranian flora. It is a very good plant, has got many medicinal effects on human, and my friend and other colleagues are working on it. We work on this, the essential oil of these plants against two mosquitoes, Anopheles stephensii and Culex pipiens. The LC50 values of this plant against these two vectors is, you see the figure is 2.69 ppm, which lies in the highly, and about the Anopheles is 4.88. It's highly active class. I'm going to work on this. It's very simple screening. You see, I've done lots of work on this plant, and I'm bringing just this figure for you. We know the constituent of this all component with GC mass. We have done everything, but in this classification, I just bring a LC50 value for you. In another study, we have done a similar study on larvicidal activity of essential oil of Purpurus arizonica against Anopheles stephensii again. The LC50 value was 79.30, which again lies in the moderately active class. So we stopped working on this essential oil as a candidate for larvicide or biolarvicide. As you see, using this guideline is simple and easy and very useful for those who work on larvicidal effect of plant essential oil. You can simply screen your plants based on LC50 value and screen your subject of the study. It seems that this guideline can help researchers to separate active plants from non-active in this regard, and can help to make a priority of them. Thank you for your time and your attention.
Can you elaborate very briefly on the assay itself? Like, how do you apply the volatile oil to spray?
Well, actually, we conducted research on around 50 or more extraction of plants and essential oils of plants against Anopheles vectors and other mosquito vectors. And alongside these studies, we go through the lots of articles. We've done it through review systematics, study, and based on these materials, we can provide this classify or classification.
But your original research that you presented here, like on the
Yes, this is a classification.
classification.
Just this classification.
Just based on literature.
Yes.
Oh, so not based on actual lab assay that you conduct.
But our experiments help us to provide this classification.
Okay, this was my question. The
This
experiment
is
itself, like the experimental method itself. Like, can you describe what you do?
This is just a review. Okay. But I bring some examples of my original works here.
Which technique different research work? In Japan, we have the many spawn, okay? And of course, the mosquito egg, and then we have larva comes. And in Norwegian, we use the oil, different pens, okay? Before the larva respirate the air coming, okay, and down, coming and down. The larva is necessary the air. So the origin, okay, to use the how to say, the salad oil, okay, so that it not strong anyway. So you put the small layer, I'm not sure it's friendly, environmentally friendly or not, but the mosquito larvae completely die. This is the technique of the physical technique. Okay, this is very important. For example, we have many ponds. Okay, and then one week, for example, the defense, in your country we have many ponds, many mosquitoes, all right? But you can spray warm water warm to the pond. And then in our town, region, we have the many field of the rice field, right? And they put the eggs on dangerous. We have scheduled running water, so the rubber gone. Pond is very dangerous. So we use the oil. Do you have such an experience as an example in your country?
Yes, we used oil in the past, but nowadays we are not using oil in the environment, Okay.
Next presentation. Now I have a question. Since you have carried out a lot of experiments on screen, the mosquito,
Yeah.
I think its study is very significant. And my question is, how many plants you have used to screen this experiment?
As I told earlier, around 50 plants and essential oils of plants.
Just the essential oil.
Essential oils and whole extracts of plants.
Okay.
We have got insectaries and rare Anopheles mosquitoes, which are important for us in our country because malaria still remains in our country. So we can use these essential oils against the Anopheles and other vectors.
Did you have any potential candidate?
Yes, we have got. The Keliosa is a potential candidate, and I think it is the second one. Yes, and I think it is a good candidate for move on to next level. This is what I think.
How do you say how long? The final product.
No, I don't know.
Not yet.
No, not
how
yet.
long? Did you have got any idea for that?
I think it's a difficult question to answer. Actually, we have to work on the field. So we've done experiment in our laboratory. There is need to see what's going on the field, and after that, making good formulation and many things. I don't know when, but I'm hopeful.
Even cultivation, because the way you shoot the picture of the Kelusia, it's like a mountain plant.
That's it.
So you have to plan also the
This plant growth just in more than 2,000 meter elevation in central Iran. It's difficult to find these plants.
Okay, thank you.
Thanks a lot.